Hello and welcome to Dan Makes Things. My name's Dan, and over the last few years I've been building this guy. He's a bipedal desktop companion robot. A lot's changed since I started building this project, and I really wanted an opportunity to talk to you guys about the challenges that I've had and opportunities that I've missed. Have I made a mistake by building this in the way that I have? If I was to do it again, what would I change? I've also been asked to do a Q&A, so I asked for questions on my Instagram and Discord, and I had quite a few responses. So let's take a look at the questions and then we'll get into some detail about the project itself. One of the most common questions I get is asking about the power supply. How is the project powered? And specifically how the Raspberry Pi is powered. So let's give you a quick overview of the structure first of all. You can see in the top we have a Raspberry Pi 5 with a cooling fan attached. Then the power comes through the neck from this cable to the body, and in the body you can see, if I remove one of these panels, we actually have three 18650 lithium ion batteries. The challenge is the Raspberry Pi needs a steady 5.1 volts in order to run stably. I also have an Arduino running just below here in the body, and that needs 5 volts as well. So the way that I've managed this in order to avoid brownouts and other power delivery issues is to actually have two separate DC to DC converters. There's one behind this switch here and the other one more visible on the side of the head. This takes the voltage that comes in from the batteries, which can be anywhere from 11, 12 volts down to 9, and then converts it to a steady 5.1 volts. These DC to DC converters are rated so that they can supply the number of amps that the devices need. And because I have two of them, I have one supplying the Arduino and the servos, and the other one supplying the Raspberry Pi 5. So far, I've had no problems with power issues. You have to remember when you're dealing with things like this that you need to make sure that the ground is linked if you have any kind of separate circuits running. And in this case, because they're running off the same battery, there's no issues. If you were to run the Raspberry Pi through a power pack and then the Arduino through a different power pack, for example, or mains, you'd need to make sure that you linked the grounds between those two. Otherwise, it causes problems in your project. You can also see here that I have a USB-C input. That's a board, that's its own module, and that allows it to negotiate the highest voltage that the power supply from the USB-C cable can provide. So I can input anything up to 20 volts from USB-C and have the DC to DC converters convert it down to the needed voltage. This switch allows me to change between the mains voltage, the input from the USB-C, and then the battery voltage. You can also see in the head here, I have another USB-C board. That allows me to power just the Raspberry Pi and the head components separately, and I can do that by disconnecting this. By disconnecting that, I detach the body entirely, and it means that none of the power from the body is being used, and I can power the head separately. This is useful if I just want to work on the software in the head and I don't want to have the body moving around or the power to the Arduino in any way. While we're talking about the communication between the body and the head, you can see that there are 4 pins here. The 4 pins are positive and negative from the battery voltage, and then 2 for serial communication. The serial communication goes between the Raspberry Pi and the Arduino. Now the Raspberry Pi is a 3 volt logic and the Arduino is 5 volts. So in order to manage that, I have this logic level converter module that takes in the voltage from either device and converts a signal to the voltage that's needed for the other device. If you were communicating between 2 devices that both use 3 volt logic, you wouldn't need that. I did have another question about how long the battery lasts. To be honest, I don't run it on batteries very often because I don't like particularly having to recharge them manually. The process is a bit of a pain because you need to remove this module and disconnect it. And then you can see I've got the 3 batteries there. But I did take it to an event for the first time recently. And although I didn't have the board running the entire time, and sometimes I disabled the Raspberry Pi, I managed to get around 8 hours of battery without having to change them, and there was still a decent amount of voltage left. With these batteries, you have to make sure that you don't exceed the minimum voltage, otherwise it can damage the battery life. but I still had a little bit of a margin there before I needed to swap them out. That said, if you are looking to do some really intensive computation on the Raspberry Pi, you'll find that the batteries drain very, very quickly. In order to manage the voltage and keep an eye on the battery health, I actually have a module here which connects directly to the battery so that I can keep an eye on the battery voltage at all times. As I mentioned, the Raspberry Pi does use a lot of power, so what I can also do on the Raspberry Pi 5 is use the power button, which is just here, to be able to turn the Raspberry Pi into standby mode so that I can just have the Arduino running. So one of the other questions that I had was around the brains behind the robot. What controls it? What am I using and what am I planning on using in the future? So as I've mentioned, we have a Raspberry Pi 5 which is doing the heavy computation. We have an Arduino, and the Arduino is actually the thing that manages the servos. So although you can see it's standing and it's animating and it's even balancing at this point, all of that is done via the Arduino itself. If I was to turn the Raspberry Pi off, you should actually be able to see that the body itself continues to move and animate, with the exception of that servo. That servo is connected directly to the head so that I can have the ear connected to the Raspberry Pi using the software that's already in place. Hello. So the Arduino has a number of different elements installed on it in order to make managing the servos easier. It has something called servo easing. Now servo easing allows you to take a servo from one position to another and move it smoothly. And this is new. This has never happened before. Let's do a quick reset. I'm going to power up just the head so that we can talk about some of the functionality. As I mentioned, in the top of the head we have the Raspberry Pi. This is a Raspberry Pi 5. The previous version, which I have here, was actually a Raspberry Pi 3, a Raspberry Pi 3B+. Now the difference really in terms of the use for the project is that facial detection, facial recognition and tracking was far too slow on the Pi 3 to be real-time. So because of that, I got the Coral USB accelerator and plugged that in and attached it to the top of the head. And that worked really well. It wasn't as fast as the Pi 5, but it made it usable. We have also got an Arduino Pro Mini mounted on a custom PCB in the body. The Arduino Pro Mini controls the servos that are attached to the legs and the neck. The only servo it doesn't control is the one attached to the ear here. And that's because that's being used by the Raspberry Pi directly. I often have people asking whether the Raspberry Pi 5 is worthwhile as an investment, and broadly speaking I think it's worked really well in this project. The only problem that I have is around audio and compatibility of other modules, so I'll give you a few examples. This is a Raspberry Pi 4 with the same custom PCB that's currently attached to the head of the robot. You can see here I have a microphone, an I2S microphone, and an I2S amplifier with a speaker connected. Now the reason why I'm testing this on the Pi 4 is because neither of these things work on the Raspberry Pi 5. These are both Adafruit, and although Adafruit is aware they don't work on the Raspberry Pi 5, there is no mention of a fix or timescales for a fix, despite the fact that the Pi 5 has been released for quite some time now. Similarly for the NeoPixels, I chose to do I2C NeoPixel control using an additional module that connects to these pins on the back of the board and then control all of the NeoPixels via the I2C. The reason behind doing that was that when I tried this on the Pi 3, there was a decision to be made. If you had NeoPixels connected to a Raspberry Pi, you needed to disable audio output. Now that was either for a specific pin controlling the NeoPixels or just in general, and I never quite found out what the reasoning behind that was. So I went for the I2C. But it was fortunate that I did so, because actually on the Pi 5, the NeoPixel software isn't supported yet. Now I've been involved in the conversation around this, and it isn't just a simple fix. The reason behind it is that something fundamental has changed in the architecture of the Pi 5, which means that the NeoPixel software won't work until something has been resolved in that area. So it's something to bear in mind. If you're looking to get a Pi 5, just make sure that the modules that you're looking to use are compatible. because at the moment I can't use microphone or audio output with the Raspberry Pi 5, although I'll also say that compatibility on the Pi 4 isn't fantastic either. I've spent quite a bit of time trying to get these things working in a reasonable way. Which brings us to our next question, which is it worthwhile having the Raspberry Pi and the Arduino, or would we use a different architecture? One of the things that get mentioned quite a lot when we have this conversation is things like the ESP32. This is almost like a super-powered Arduino board. It has Wi-Fi and Bluetooth, and is a lot more powerful than the Arduino Pro Mini. It's obviously not as powerful as the Raspberry Pi, but it also doesn't need to run a full operating system on it. So there is an alternative here that we take a board like this and insert that in the body instead of the Arduino, and then do away with the Raspberry Pi itself. You can get ESP32 cameras that connect either to this or to their own board and then can communicate via I2C or some other protocol. And that would mean you wouldn't need to have a camera and dedicated software running the camera recognition. There are also modules like this. This is the person sensor by Useful Sensors. And it is a camera in the same way that I have a camera already mounted to the head, but this one has an onboard chip that takes the input from the camera, detects faces, and relays information about the position of those faces via I2C with these two wires. And so what it means is that you don't need to have all of that happening on the Raspberry Pi with all the power requirements that are involved. You can connect the person sensor to an ESP32 and still get positioning of the faces and still move servos to track that if that's what you're looking to do. Now obviously you can't take the person sensor and reprogram it to detect objects or to track specific things that you'd want it to track. It only works for the given use case. But if that's the bounds of your project, and for most people who are just looking to kind of take these things to events and have a bit of fun, really that's probably all you need. I've been working recently with the ESP32 just to understand what its capabilities are and what the module's support is like. And so far things are looking quite good. So I may look at creating an ESP32 version of this robot in order to make something that is lighter weight, maybe smaller, and maybe has a similar level of support for the functionality that I'm currently using on the project. And we'll talk more about functionality in a minute. I often get questions about which software is being used on the project and what frameworks I have in place. So the Raspberry Pi 5 uses Python, and it's basically custom software to this point. Now, I spent quite a bit of time putting together modules so that I could build all kinds of different functionality for the project. And each one of those needed its own Python script. Those Python scripts were then combined so that I could run everything within a single Python file and have events and timing and input from the various sensors in order to make the robot behave the way that I wanted to. And this all worked reasonably well. But these days there are frameworks that'll do a lot of that heavy work for you. One of the most popular ones is ROS, or now ROS2, which is the Robot Operating System. And you can get modules that you would normally have to build yourself from scratch and install them in a few minutes. The challenge behind ROS is that the barrier to entry is quite high. There are certain technical requirements on the device you're using, not only the device that you're running it on, but also the device you're using to program ROS. And it's also quite a difficult thing to learn. And what I wanted to do was try and keep this project as accessible as possible. So I started creating a lightweight version of a similar kind of thing. I recently came across Vim, which is a framework that allows you to configure your robot online. It gives you additional functionality that you wouldn't ordinarily have from custom scripting. And it also has a modular registry that allows you and other people to share modules with each other in order to leverage work that has already been done by others. Investigation around this is still ongoing, but I have had some pretty good success with the modules that I've created so far, and I'm excited to see how things develop with the Vim framework in future. Vim also allows you to use multiple languages at once because of the communication method between those modules. So if you have something that is particularly computationally intensive and you'd rather use C than Python, you can do that and have the rest of your script still running in Python. You don't need to rewrite the entire thing, which is excellent. The Arduino, of course, is using the Arduino language, which is based on C++, and the script there is starting to get more complex than I'd like it. I'm probably going to look at rewriting that into a package in the future. Let's talk about functionality. What can it do? So the robot has a number of modules that I've put in place, and I have to admit that so far I haven't focused too much on merging those into a single cohesive behavior for the device. What I've been looking to do is make sure that each of those modules will work as I expect it to work. So for example, I have facial tracking, I have object detection, I have object tracking, there is a microwave motion sensor which can detect people even through walls, and so I've made sure that that will work as its own module and allow it to detect people and behave differently based on whether there are people present or not. As I've mentioned, we have the microphone, we have the amplifier, we have the neopixels, we even have some more quirky things like this, which is a laser scanner that can be plugged into the head and incorporated. I've decided not to include that for reasons we'll talk about later. Scripting and functionality in order to make the legs work has taken quite a lot of time. There is an inertial measurement unit, the MPU 6050, integrated into the Arduino PCB, and that allows it to keep check on how the body is positioned and then balance and adjust accordingly. So as it stands, it should be able to stand indefinitely, even as the head moves and shifts the center of gravity. It also has inverse kinematics. Inverse kinematics is an algorithm that allows you to specify the position of the feet relative to the body and have the calculation for the servo positions be done automatically. That is in place, although only in terms of the height of the leg. And I find that the calculation is very restrictive and the range of motion is actually greater than the calculation allows it to be. So there's work to be done there as well. There is an integrated voltage management on the Arduino so that we can actually understand and react to the battery voltage via software instead of manual monitoring, and a number of other smaller things. And you'll find that as you start working on software like this, it can take a long time to get it into a position where you're comfortable with moving forward. One of the advantages of migrating over to VM is that a lot of that work has already been done, so I'm hoping that will save me a lot of time in future. And also, as things develop, I'll be able to maintain those modules a lot easier. I also get questions around the antenna and what its actual purpose is. Now, obviously, part of the reason of having the antenna is because it looks fun. It moves, there's not really a reason for it to move. But what I do have in place is a software-defined radio device. Now, this is USB, and this will plug into the back of the head. And then this connection allows me to connect the device to the antenna and have that antenna running. The software-defined radio device allows you to monitor certain frequencies in order to either intercept radio signals or, in my case, monitor temperature stations and other devices that are located around my home. I did a short recently around this laser scanner module that connects directly to one of the JST connectors in the head. This is a simple laser diode that projects a line when it's switched on. Now the challenge with this is you can't connect some devices like this directly to the pins in the Arduino because it won't deliver enough power and it might damage the Arduino itself. So in order to mitigate that, I have a transistor connected to allow the power distribution to work directly from the voltage from the DC to DC converter, which means that I can connect more high-powered devices to the head, such as this kind of thing. Now, I did have this module connected, but I wasn't particularly comfortable with carrying lasers around. They can be quite dangerous, especially if they come from questionable sources. The rating on them may be inaccurate, and it may be that it's a higher powered laser than you expect it to be. The problem with high powered lasers is you can actually damage your eyesight, not just by shining it directly into your eyes, but through reflection as well. So I'm always very cautious to make sure that I'm not putting anybody at risk, which is one of the reasons why I decided not to include it as a permanent feature in the project. But the proof of concept was sound, and being able to have a connector that allows me to toggle on and off some singular device is actually quite useful. We could use it for a number of different things, and I have some ideas for that for the future. Let's talk about some of the questions around movement. The servos that we use are SG5010s. And I don't remember the exact stall torque on the servos that I've used, but when I was building the robot, I took the time to calculate and understand whether the servos could handle the load of the device itself. The advantage of using the servos that I have is that most of them are quite inexpensive, whereas you can get quite expensive servos that have a much higher stall torque. So if you're looking to build something bigger, just make sure that you're checking the stall torque and accommodating for that. You can calculate torque and how it applies to your device because torque is kilograms per centimeter. So that is, if something was hanging from the servo 1 centimeter away from the center point, that rating is how many kilograms it could hold. Therefore, if it was 10 centimeters away instead of 1 centimeter, the rating would be 10% of whatever is rated as the stall torque. As far as controlling the servos, we've already talked about the fact that the Arduino is connected directly to the servos in order to manage those, and I have a custom PCB to manage this. But if you ever have challenges and you'd like to do something like that yourself, you can do it quite easily using another module which is called the PCA9685, and it's a 16-channel servo driver. You can connect via I2C to the device with either 3 or 5 volts, and it allows you to then power the servos from an external source and control them all individually via I2C. I'm using one of these in my next project. The real reason for using Arduino is I wanted the option to be able to disconnect the Raspberry Pi and just have the Arduino animating by itself. Now obviously without the Raspberry Pi or another controller, the PCA9685 wouldn't do anything. The Arduino is able to manage things by itself. The next question is around the gears on the legs. We could make it so the servo is connected directly to the pivot point on the leg itself. And in fact I did this in an earlier version. The challenge that I found there was that the whole device wasn't strong enough, because you need to accommodate and integrate the servo in such a way that it was constantly slipping or the screws were working loose. By building it this way, I've been able to build a much more sturdy leg mechanism. You can see that we have bearings in those pivot points, and then we're able to swap out the gear ratio as well if we'd like it to be stronger or weaker or a slightly different ratio to what we have at the moment. You can see I'm using herringbone gears here in order to try and stop them from slipping, but it's also important to mention that there is a reasonable amount of space between them. You can see as the leg will move slightly without the servo moving, and that's deliberate, because during development it was important to make sure that I wasn't putting any unnecessary strain on the servos, so a little bit of wiggle room has helped me stop burning them out every now and again. And in fact, during the entire development of the project, I've never burned out a servo so far. The balancing mechanism, as I mentioned, is the inertial measurement unit, the MPU 6050. Now, I'm not specifically recommending this module. There are others that will do similar things, depending on what your availability is like in your area. But this allows us to monitor and understand the position in multiple angles of the device, and that will allow the body to remain level at all times. It does that by basically adjusting the offset of this servo and the one on the other side, the hip servos, and that allows it to keep the body horizontal regardless of what the rest of the robot is doing. Without a doubt, the most common question I get from new people who haven't been following the project for very long is, can it walk? The reality is it can't. There is progress in that area. This version of the project is a lot easier to make walk than the previous version, because the previous version couldn't support the weight on a single leg. Part of the reason for the redesign of the legs was to see if that was possible and see if that was something that we could do. We also have hinging at the hip joint, which allows the leg to move inwards. So theoretically, we could have it standing on one leg. The leg itself has accommodation for a raised strip of something there so that it can balance on a center point. So there are steps that have been made in order to try and facilitate that. But I'm not going to pretend that making it walk was ever really one of the goals. The idea behind this was to make a desktop companion robot, something that you could interact with, that would be primarily mains powered, and something that would be fully autonomous. Even ignoring the technical challenges behind making the legs walk, we'd need then to solve the problem of how it navigates and how it finds its way around a space with a single camera and no other inputs. And there are ways that you can do that. It's an interesting challenge, but it isn't something that I'm particularly focused on with this project. That said, there are quite a few people in the community who are interested in seeing that happen, and they're working towards doing that in their own time. If you're interested in seeing it walk and you'd like to build your own to try that out, then by all means join the community and join that conversation. Recently there's been a robot demonstrated by Disney, which people are calling the duckling droid, that has a very similar form factor to this robot, and that's probably because they're both based on BD-1 from Star Wars Jedi Fallen Order. They've managed to make a robot that will walk and will move around and goes to the theme parks and meets guests and interacts with them. And the way that they've done that is by salvaging extremely expensive brushless DC motors. And they've built something that is a lot larger than this in order to facilitate that kind of movement. Since the release of that video, there have been a number of people who are really interested in making their own version of that. So there is an entire community built around reproducing that walking robot from Disney. So if that's something that you're interested in looking at, join the Facebook group. I'll link to it in the description so you can get involved in that discussion as well. I get questions around whether I've considered using other form factors in order to manage to make the thing walk, whether I'd like to attach wheels to the bottom of the legs. In truth, the form factor of the robot is because I wanted it to be based on that design. Wheels on the legs would be excellent and easy enough to do because you could swap the ankle servos out or even use continuous servos and pin the ankle joint and have a single wheel. You'd be able to make a balancing robot that balanced once it was up, and then when it was sitting it would rest and wouldn't need to have the wheels powered. So that could be something that would be an option. You would need to be able to control it and allow it to move around, but as we've mentioned, devices that have Bluetooth like the ESP32 would allow you to facilitate that as well. So that is definitely something that could be an option for the future. That way I could take it to events, put it on the ground and drive it around using my phone. People who are new to the channel are often asking how they get started building their own. I've spent quite a bit of time putting some of this information together on a wiki page that's connected to the repository, but the best place for you to get started is to go to makerforge.tech and take a look at the Modular Biped project page. It has an introduction to the project, details of all the YouTube videos, and then links to not only the GitHub repository, which contains the source code, but also the wiki page, which goes into a ton of detail around which components you need, how to get started, where to find the 3D prints, and so on. If you find there's something not included in the wiki that you'd like to see, join the Discord community and get me to include it. I'll gladly update the wiki page as often as needed to make sure all the information is there for everyone. As far as changing the design, everything is open source, so I'm more than happy for people to make changes as they see fit, take certain components or modules and use them in isolation or with a completely different project itself. That's all completely fine. We'd love to see what people are doing with the project. So again, feel free to join the Discord community and let us know what you've been working on with this project. We have people who are using different single board computers or different microcontrollers, who are incorporating different battery types and different designs, and a little bit more outlandish ideas as well. I'd love to be able to teach everybody how to build something like this, but unfortunately I don't have the availability to do much more than I'm doing right now. So a lot of people will send me messages and ask for mentorship or for some ideas or how to get started. And if you'd like to get advice on how to build robots in general, there's so many resources available on YouTube. I should say, if you don't already know this, that I started out as a software engineer. I had no knowledge of robotics or electronics before I started this, and I found out everything that I learned through YouTube. So it's a great resource and something you should definitely take advantage of. Something like this is far too complex to manufacture and sell. It's not something that I would ever consider doing. You need to have a certain level of technical expertise in order to be able to assemble it, let alone program it and make it do what you want. So it's not something I would ever consider selling as a kit. It is available as open source, however, so you should definitely be able to take a look at doing it yourself. People who have been involved in building the project for a while will know that there are some recent changes. We covered that briefly a few minutes ago when we were talking about this build. This was the Raspberry Pi 3 version. Now the changes since for the Raspberry Pi 5 is that we've dropped the Coral USB accelerator. We've also dropped the custom PCB, which is hidden underneath this section, and we've migrated away from a few of the other components. The new custom PCB includes all of the functionality that I wanted the robot to have on a single board. It's as compact as I could get it without making custom modules myself, and allows you to swap things out, hopefully as easily as possible. The antenna is obviously very new as well, and is the first servo controlled directly by the Raspberry Pi. Besides that, very little has actually changed. We've updated some of the 3D prints. in order to make the range of motion better on the legs, for example, where this knee joint previously could only bend at 90 degrees. But all of those updates are fairly optional. We've also already talked about the benefits of Pi 5 over the Pi 4 and other restrictions and challenges. As far as general questions, there was a question around if there's an end goal to the project, or if this is just a continual development. And to be honest, I never intended it to be as long of a project as it was. The beauty of technology is that things are always moving forwards, so there'll always be some way that I can update this, add new functionality, add new features, swap out the Raspberry Pi for a faster board as time goes on, as I've already done. Really, I'm just enjoying the journey. I'm really pleased to see that other people are as well. Now let's move on to the final question. Did I make a mistake in building the project? Would I do anything differently if I could go over and do it all again? I think that completely depends on the goal of the project. When I took this device to an event, I was able to put it into a very restrictive kind of demo mode. And the demo mode would allow it to stand and balance. It had a switch so that I could put it into a position so that I could mount it in a backpack. It had a time lapse running on the camera so that it could take images periodically so that I could stitch them together and make a time lapse for the event. And it generally just moved and animated very similarly to what you're seeing the head doing now, with the body looking around at random intervals as well. Now, if that was the extent of the project and that was all I wanted to do, then a lot of the work that I've put in place wouldn't have really been necessary. The Raspberry Pi is definitely overkill for something as simple as taking time-lapse footage, and it is far too power intensive for something like that. But what I wanted to be able to do was have the full flexibility to be able to build something very different as time went on. So as I found out about new functionality and availability of new technology, I could put that in place. Now, if I'd used an ESP32 or an Arduino by itself, I wouldn't have had that same flexibility. For example, you can now get large language models that you can run offline on a Raspberry Pi. The Raspberry Pi needs to be sufficiently powerful and have enough memory, but you can execute the code and have them running. And that means that if I incorporate a microphone and speaker, I can ask questions to and get realistic answers back. That's something that didn't exist at the time that I started this project. It's really exciting to see the technological advances that are happening that I can leverage in projects like this. Arduino has been great and it's worked really well, but I am starting to see limitations around the computational power of that microcontroller. ESP32 is far more powerful, and the addition of Wi-Fi and Bluetooth means that I can do a lot more with it without needing to rely on the Raspberry Pi itself. So I'm interested to see whether that kind of thing would be beneficial rather than using an Arduino in the body itself. The problem then is that the PCB is built around the specific version of Arduino that I've used, so I'd need to build a new one. I could also take a look at other devices like the Raspberry Pi Pico, which has similar functionality and is also very accessible. So broadly speaking, I'm very happy with the project. It's been great to see the interest it's generated in the community, and I'm looking forward to seeing what we as a community will build on this in future, as well as leveraging new components and frameworks as they become available in the future. It's definitely a long-term project that I'm looking at building on and improving as time goes on. I will undoubtedly have breaks from the project to work on other things, but I'm really pleased that it's something that I can keep coming back to and building on as I go. And most importantly, I've enjoyed the process of learning everything that I have during the various iterations of this build. If you didn't get a chance to ask your question for this Q&A, feel free to send it over, and I'll try and get to it in one of the following videos. Thanks for watching.